Okay, can you hear me? Okay, thank you very much, and thank you, Barbara and Nicola, for organizing this nice workshop. And what I would like to present you today is some results about anisotropic imaging of the mantle and applications to oceanic and continental lithosphere, asthenosphere boundary. And I mentioned two PhD students who work on that and some colleagues who also participated to this work. Okay, so the outline is, of course, what is a plate, what is a continent, and I will try to demonstrate that seismic anisotropic will enable to gain insight into these scientific issues, but I will show as well that there are some different processes can give rise to anisotropy. And finally, I will apply to ocean, continent, with the example of the Indian continent. And if I have time, I will show that we have some result about anisotropy in the mantle transition zone. Okay, so that's a classical figure which show the different way to define the lithosphere, asthenosphere boundary. I don't want to detail, but well, you know these different points. And of course, I will be primarily interested in the way seismologists can investigate this issue by considering the velocity profiles and the fact that we have a high viscosity, high velocity lead above the low velocity zone. And from seismic anisotropy, we can expect that when we move from a lithosphere to the asthenosphere, we have also a change in anisotropy. So it is what we will try to look at. So for students people who are not familiar with seismic anisotropy, I want to remind that seismic anisotropy is present at all scales, from the microscopic scale at for olivine, which is the most important mineral in the upper mantle, which is at 10⁻⁹ meters, up to the very large scale. And it's a long way from the microscopic scale up to the seismic measurements. Here I show only the first anisotropic model, the PREM model, with anisotropy in the uppermost 200 kilometers. But from the microscopic scale up to the large scale, we have other processes which can give rise to seismic anisotropy, and I will rapidly detail these processes. And it is classical now to distinguish intrinsic anisotropy, which is present whatever the scale. It is basically related to mineralogical anisotropy, and extrinsic, which is more processes which give rise to anisotropy by mixing different media and layering and so on. So we have these two kinds of anisotropy. Both give rise to apparent anisotropy, and so a basic issue is to discriminate between intrinsic and extrinsic anisotropy. Most of the time, we interpret anisotropy in terms of intrinsic, and this morning, Thorsten showed that if we consider CPO, which is a crustal preferentiation, it is the preferred interpretation of anisotropy. Okay, so it is present at all scale. We have to understand 15 orders of magnitude, but of course, what we observe is only from seismic waves. Lambda W is a seismic wavelength, and of course, you see that the 15 order of magnitude, and we have only access to the longest wavelength. That's the reason why what we observe is an apparent anisotropy, and so it makes quite difficult to explain in a simple way anisotropic observation. And as is what I said, seismic waves are myopic, so we don't see very carefully the real Earth, because we only see the long wavelength Earth. And of course, that is the upscaling, but for the downscaling, we can use seismic anisotropy for investigating different phenomena. And of course, the most classical one is for mapping convection, but also we have seen this morning that it can be useful for investigating the melt. And even what should be great is to be able to find the mineralogical composition of the Earth by using the whole elastic tensor, which is not so easy. So let me remind again why it's important to look at crystal preferentiation. Before it was named lattice preferentiation. So it is a classical figure where we have olivine and also another important mineral, orthoperoxine. And olivine, the fast axis, tends to be parallel to the flow direction, and the slow axis is perpendicular to the flow plane. And you see that the difference between basically 10 kilometers per second and 7.7 is more than 20%. So it's not a small effect. It's really a very large effect of in terms of anisotropy, because we have about 20%. And when you add other minerals, which are not so as important as olivine, but who are present in the Earth mantle, of course, you tend to slightly decrease the amplitude of the apparent anisotropy. But as you can see, a basic application, the simplest application of anisotropy is to map convection. Okay, so, I did a mistake. Anyway, we have other phenomena which are what is named the shape preferred orientation, and I show two examples in the crust, but not only in the crust, also in the lithosphere and the asthenosphere. When you have melt, when you have a stress field, you tend to open or to close some fluid inclusions or cracks, and it is very useful for investigating the stress field. And whereas the previous CPO was more sensitive to the strain field, and this phenomenon is present not only in the crust and in the asthenosphere, but also we propose that it is also present in the inner core, where we might have some layer with fluid inclusions of iron. So you see that we have two different phenomena, CPO and SPO, and an extreme case of SPO, which is due to a very elongated layers. It is a stratification anisotropy when you have a fine layering, and it was proposed by Kawakatsu more than 10 years ago, that in the asthenosphere we have this layering with a solid and mixing with a melted layers. And in that case, it is the simplest case of anisotropy, so it's quite theoretical. But in that case, we have what we call a vertical transversely isotropic medium. We have a vertical symmetry axis, and we need 5 parameters. I remind that for isotropic medium, we only need 2 independent elastic parameters, which are basically related to Vp and Vs. But when we have the simplest case of anisotropy, we need at least 5 different elastic parameters. Okay, so we have different processes which are related either to stress or to strain. As I told you, the most important is probably CPO, but it's not. These different processes are present in the different layers of the Earth. And so if we are able to discriminate these different kinds of anisotropy, intrinsic in the center and extrinsic, we will gain insight into different processes, and we can have information about, of course, present-day tectonics, mineralogy, water and fluid content or melt, and also on past processes in mountains, for example. We can look at frozen anisotropy. And another important application, which is quite recent, is it's a way to monitor the temporal change in stress and strain field by looking at the temporal change in seismic anisotropy. Okay, so as I told you, the main difficulty is to separate these different kinds of anisotropy, and so we can have different interpretations. So it's good when we have different interpretations, a lot of debate, which is quite nice. And what I will show only one transparency about the theory. I don't want to detail the calculation, but very often students are scared because we have to use a fourth order elastic tensor, CHGKL, and so we have to make these complex tensor products. But finally, we come up with this simple expression where for phase velocity of surface wave, but also for group velocity, we do a Fourier expansion of the phase velocity as a function of the azimuth. Azimuth is the orientation of the path between receiver, between source and receiver, and we have different azimuthal terms, 5 azimuthal terms. And what is nice when we do this simple theory, we can calculate the sensitivity kernels of these different azimuthal terms. And so from a practical point of view, what we do is to derive the geographical distribution of these different azimuthal terms, alpha 0, alpha 1, and so on, and alpha 4. To continue on the only theoretical point of view, there is a, yes, it is a psi here, but it apparently does not come. Okay, so of course we have different azimuthal terms, and we cannot retrieve for surface wave, we have 13 parameters, and we cannot have access to these 13 parameters. So basically, we have only access to the isotropic part of Vs velocity, the radial anisotropy, which is the ratio between VSV and VSH square. It is a psi here. And the azimuthal anisotropy, which is the azimuthal variation of S-wave velocity. And by the way, we demonstrated that it is also this G and psi G parameters are also related to body wave anisotropy. And so if we can retrieve this parameter, we can have constraints not only from surface waves, but also from SKS waves. Okay, so a simple interpretation in the case of CPO, which is very easy to understand. From anisotropic imaging, we have 3 different kinds of maps, and if we imagine that we have a convective cell with upwelling and downwelling, I show some horizontal cross-section here. And of course, we have SV velocity, radial anisotropy, and azimuthal anisotropy. And so if we have these 3 pieces of information, we can map the upwelling and the downwellings. For example, Vs is if you have an effect of temperature, we have slow velocities when you have upwelling, fast velocities when you have downwelling. But for radial anisotropy, you can discriminate, because what is important for radial anisotropy is to know if flow is upwelling or vertical or horizontal. And so you have these 3 pieces of information, and you can map by using anisotropic imaging, mantle convection. Okay, so of course we need data, and the most famous data are, of course, shear wave splitting, and the famous effect that when a S wave enter an anisotropic medium, you split the waves into 2 waves, propagating at 2 different velocities. And if we measure the delay time and the orientation of these waves, we have access to the average anisotropy. And the SKS is nice because it's propagating, it is a converted wave from P to S wave, and so we know the initial polarization, which is not always the case. Of course, what I will show you is results from surface waves, and it's a long-standing result that there is a discrepancy between Rayleigh and love wave dispersion curves, and it was necessary to introduce what is named the polarization anisotropy. But since in the 60s, this first discovery, and now what we retrieve is at the same time azimuthal variation of phase or group velocities. And another effect which is quite important and is more complicated is that when you have seismic anisotropy, you change the amplitudes of, and you have no longer Rayleigh and love waves, but you are quasi-Rayleigh waves and quasi-love waves, and its interpretation and modeling is much more complicated. The reason why we, that's I guess, I don't know if it is the last database compiled by Thorsten Baker, but you see here that we have a lot of measurements of SKS in the whole Earth, except that we have very few measurements in oceans. So that's a simple reason why we need to use surface waves to investigate anisotropy below oceans, because we have very few measurements of SKS, and we need some ocean bottom stations to do it. Okay, so to go back to this lithosphere acidospheric boundary issue. As I told you, I will focus on VS and anisotropy. And there was a long-standing debate about what is the lab below continents. And there was a discrepancy between receiver functions and surface waves. From receiver functions, they map something, a discontinuity around 100, 120 kilometers, whereas from surface waves, the continental route was down to 200, 250 kilometers. And the way to solve the issue was done by Barbara Romanowicz and her group, where she showed that the structure of continents is much more complicated than what was thought. It's not one layer, but we need at least two layers, and we need to introduce some discontinuity or some low velocity zone within the continent. And so that's the reason why you see different parts of the continent when you consider receiver functions or surface waves. And so what I would like to show you is that some years ago, we decided to work on oceans, and by using surface wave. Of course, it's not so easy. We use different techniques. We compile a lot of dispersion curves, fundamental mode, but also higher modes, and we use a statistical approach, and we use also a classical first-order perturbation theory, but in an anisotropic medium. And the idea for this surface wave, we have no resolution of discontinuity, but we did the assumption that if you have a discontinuity, you have a gradient, and so we say that when you have the maximum of the gradient, we have access to the discontinuity, and we make this strong assumption that we have access to the lab through the gradient of S-wave velocity. Okay, so let me show you in only some results. I already showed that some years ago here. And for the isotropic inversion, by using Monte Carlo statistical approach, we find this kind of map for the lab, and we find what we expect. I mean, a shallow lab for oceans and mid-ocean ridges, and a deep lab for old continents. And so nothing really new, but what we were expecting from plate tectonics and geology. And when we do that from the gradient of S-wave velocity, actually we find the same kind of geographical distribution, but different depths. I mean, the same thick cratons and shallow mid-ocean ridges, but cratons have deeper roots compared to what was obtained from isotropic inversion. And finally, what was the most surprising was what we found from radial anisotropy. As you can see from radial anisotropy, and again we use the gradient of radial anisotropy, and we only limited this inversion to oceans because in continents it's much more complicated. But what we found is that the maximum of the gradient is always at the same depth, very small variation, except close to the mid-ocean ridges, but basically it's always the same depth, which was quite surprising. And of course, we checked these results for different oceans, and we always found the same maximum. And so if we consider these three maps, isotropic S-wave velocity, anisotropic VS velocity, and radial anisotropy, we have for S-wave the same kind of geographical distribution, but a different depth for the different geological objects. And it means that it's important, and it was emphasized many years ago, for example, by Don Anderson, that when you do an isotropic inversion and an anisotropic inversion, of course, you will change the depth of discontinuity of the lab, and you will affect the seismic profiles. The last map is quite interesting because, of course, as I told you, it was completely unexpected, and it seemed that within the oceanic plate we have some discontinuity or a change in the properties of radial anisotropy. And of course, we look at the classical model of plate, half-space cooling model, which is quite old and which cannot explain what we observe. We have a Monte Carlo inversion, we have a perturbation theory inversion, and we have radial anisotropy and azimuthal anisotropy. I did not discuss that point, but it was also derived. Of course, when we consider the plate model, it's much better. It's not perfect, but we have something which is not so bad for the base around the isotherm of 1300 degrees Celsius. But for the radial anisotropy here, the Xi parameter, you see that the depth variation is very small and it does not correspond to a specific isotherm, but basically it is within the oceanic lithosphere. And what we observe for the Pacific Ocean is also observed for the Atlantic Ocean and Indian Ocean. And again, the plate model is not so bad. It works fine with the 1300 degrees isotherm, but again, for radial anisotropy, this kind of mid-lithospheric boundary. And so, of course, I am not a geologist, and so I don't know how to explain this data, but people say that, of course, we have a difference between the 50 or 60 kilometers of mid-ocean ridges where you have melting, and this discontinuity might be some kind of inherited boundary due to what happened at below mid-ocean ridges, and we have the upper plate. We have incoherent large-scale anisotropy, and below the lower lithosphere, where we have more coherent large-scale anisotropy, and even below we have the asthenosphere, where we have again a large-scale coherent anisotropy. So let me try to go further, and for oceans, I will move to continents. And so what is important at this stage is that we have shown that the structure of oceans and continents is not so easy. So we wanted to look at a specific case, which is the Indian continent. The reason for that is that there was also a debate about the Indian continent, because this Indian continent is unique in many respects. Before the collision with Asia, it moved at about 20 centimeters per year after its breakup from Gondwanaland. Indian continent is not so large, but you have 5 different kinds of cratons, and of course we can wonder if there is a role of hotspots, because of course part of the Indian continent you have the Deccan volcanic trap, and there is also on the other side the Rajmahal volcanic trap on the other side of the Indian continent. And so it was interesting to try to address the issue of the continental structure of the Indian continent. And even for the Indian continent, some people in India say that this supermobility is due to the fact that it is a very thin continent, and there was some papers about that, but of course now that it was before it was discovered that there was this mid-lithospheric discontinuity. So we tried to look at the Indian continent and to see the structure of the Indian continent. And yes, I would like to mention that the group of Prakash Kumar proposed that there is also some large topography of the lab due to the post-collisional flexuring with after collision. Okay, anyway. So that's the geological structure of the Indian continent. Of course, in the north, we have Himalayan belt and Tibetan plateau, and you see in purple these different 5 cratons overlaid by the Deccan volcanic trap. So it's a small continent, but quite complicated. And we were very lucky because we had access to a lot of data. You see that India is a very secret country. It's very difficult to have access to seismic data, but they have a lot of broadband seismic data, and that's the example of the seismic network we were able to use to make this study. Okay, so I will move to the results. And from surface wave, Rayleigh and Love waves, at 70 kilometers, what we see that in the north we have Tibet, and not surprisingly, because we are still in the crust, so we have low velocity, but when we go deeper, you see that now we have a fast velocity in the whole Himalayan and Tibetan plateau. And within the rest of the Indian continent, we have azimuthal anisotropy, we have oceans here, we have some fast velocity, and you see here that in the middle of the Indian continent, we have these fast velocities. And I also present you rapidly some results about the radial anisotropy, which is not so interesting because except in northern India, where we have strong anisotropy beneath Central Asia, basically the amplitude of radial anisotropy is quite small, except in some specific spots, such as the Deccan volcanic trap or the Raj Mahal traps. Okay, so let me go back now to some cross sections. Okay, there are many cross sections. I don't want to detail all of them, but we have basically east-west cross section here, K1 and K3, and southwest northeast cross sections. And you see a large variability. It is the first result of the study that, according to the cross section, we have very large variations, and we can see that if we look at the depths of the cratons, we have this specific shape here of the Indian continent. And I will detail in the next figure. How much time? 5 minutes? Wow.
No, 5 minutes for the question.
Okay, I have to okay, I will complete this Indian continent. Anyway, you see here X5 is southwest northeast, and you see that we have this deep route around 250 kilometers and the subduction, and it is the same for X3, X4. So we have we can see that we have two different cratons with different depths. The EDC is one craton, and this one CY is another craton. We also see some low velocity zone within the cratons, and this figure is quite interesting because in that case it is K3, K4 to basically east-west, and we see that we have this low velocity zone around 100 kilometer depth, but this specific keel here and the subduction at in Burma. And so it's quite interesting because it seems that we have this shape. In the north-south direction, this is more flat. And what we see is that if you look at the lithosphere-asthenosphere boundary, we have this map. And we have at the same time, that is a filter, that is a rho direction. And we see this keel here, which is basically southwest, northeast, and the orientation of anisotropy around this keel. And so we can wonder what is the role of this keel. And what we propose is that this keel is like when you have a boat, you have a keel, and so this prominent keel is important from the geodynamic point of view because the shape and the orientation of the keel along the direction of the motion is probably play an important role in the geodynamics. And other issues we would like to address is, of course, to understand if there is a relationship between the orientation of the keel and the plate motion, but also what is the plume influence on the fast place velocities and how is it related to the plume of La Réunion. So, okay, so what we show is that for the Indian continent, large variability of craton thicknesses, this evidence of low velocity zone, and the Indian keel, that is probably the most interesting result, that we have to understand what is its geodynamic role. Okay, I guess I will not have time to continue. I wanted to show you that we can investigate anisotropy in the transition zone, but I guess I have to stop here. Okay, thank you very much.